our discussion. You remember we started talking about the string scattering amplitude, and we got to the point where we felt quite happy with our understanding of the formula for the amplitude, except for the quantity for the question of what we should insert into that amplitude. That was not completely satisfactorily understood. We knew that these V's had to be dimension 1, 1 primaries, but it seems like there were too many 1, 1 primaries. You could make oscillators out of 26 X's, then there were the B's and the C's. And should we put some arbitrary restriction? If we do that, will we lose unitarity because other things that we did not restrict to will run in intermediate states? This is the kind of worry we had. Okay? And so we're going to use the formalism of the BRST symmetry to address this worry and to find the clear set of rules for what to do in this lecture. Okay. So I'm going to very briefly review the basic idea of BRST, the BRST symmetry. Okay? Consider a theory where the fields in question, whatever they are, we'll abbreviate them. We'll use abbreviated notion. We'll call these fields phis. Okay? Let's say we call them phi i's. Maybe phi alpha. Okay. And consider a theory in which there's a gauge invariance. No, let's call this phi I. So we consider the theory in which there's a gauge invariance such that under a gauge transformation, phi, the change in phi is given by delta alpha phi. Some change. Okay. Now, let this gauge transform. This is a regular gauge transformation. So it's based on some Lie algebra, possibly infinite dimensional. Let the structure constants for this Lie algebra be given by delta alpha delta beta is equal to f alpha beta gamma delta gamma. Okay, so the discussion I'm going to give is very general, and then we will first give the general discussion and then apply it to the particular case of the string. Okay, let me just check if Pulchinski puts an I here. No I. Good. Okay. Now, what we want to do is this. We've got some action which is a function of the phis, and the phis have the property that they are gauge invariant. I mean, this action has the property that is gauge invariant under gauge transformations of phis. So make an infinitesimal transformation of the phis by this delta alpha phi, and that action remains unchanged. However, because of this gauge symmetry, in order to write down the path integral, we had to fix gauge. Okay? So suppose that the gauge fixing we did was of the following form. We chose some number of functions fa, and we said fa of phi is equal to 0. This is the condition that, in gauge orbits, picks out one configuration per orbit, the zeros of this fa phi. Okay? Now, what is the path integral that we would get if we worked with this way of thinking? I'm just going to repeat this. It's basically the logic is the same as what we worked out in class, but I'll quickly repeat it so that you get used to this logic. The thing that we started with was d phi exponential of s of phi, the minus sign. Okay? And we really wanted to evaluate this modulo vol of the gauge group. Then we introduce the following the following identity. 1, just 1, the number 1, is equal to the integral over the gauge group delta of f of phi f of phi. Now, phi is this special value such that at that special value f of phi c is equal to 1. Okay, so this phi
0.
What?
F of phi c
Is 0. Thank you. So phi whatever, phi c, and then omega minus How do we do it? We've set phi. Phi. Yeah, actually, let's just do this. Let's introduce delta of f of phi omega equal to 0. Okay, times this delta Faddeev-Popov, which this Faddeev-Popov will now be gauge invariant function of this phi. Right? Okay. Now, by gauge, as we did in class last time, we'll make a change of variables to show that this thing here, this integral here, is a gauge invariant function of phi's. We do phi goes to phi times omega prime. This measure is invariant under the omega prime. Okay. So in particular, we can move this phi to the value phi c, which is the 0 of f. Okay. So this delta fp will be a function only of that phi c. You know, that's the function of which orbit. Okay. And we've got this object here. Okay. And now, as before, we work out the expected so it follows the delta fp. Okay, so I should write two formulas here. First, the first formula was here, but then this is equal to d omega delta of f of phi c omega is equal to 1 by delta fp. Let me just expand this f around in a Taylor expansion to first order in omega around identity. Okay, we know that. Okay, so what do we get? So we get 1 by delta fp is equal to integral d omega, where little omega indicates infinitesimal gauge transformations. Okay, so however many there are, infinitesimal gauge transformations, then delta of, now what? F of phi c plus del f by del phi I. Exactly. Delta of delta alpha. So these were omega alphas because those are the number of gauge parameters. Delta alpha of phi I, okay, times omega alpha. Right? But this was 0 by definition. F of phi c was 0. This derivative is taken around phi equals phi c. And so this is 1 by delta fp is equal to d omega alpha delta of del f by del phi I delta alpha phi I omega alpha. And therefore 1 by delta fp is equal to integral integral exponential of some I lambda I, now d omega I d lambda I lambda, I'm just exponentiating delta function times del f a by del phi I delta alpha phi I times omega alpha. All good? And then we use the usual trick. So delta fp is that same integral, but with all both, because it's a quadratic integral, quadratic in lambda and omega. We just replace it by the same integral, but over fermionic versions. So dBA, this is really functional integrals. It's, you know, these things would all be position in space dependent. These I coordinates include positions in space. These alpha coordinates. Right? I mean, because we'll be applying it to gauge symmetry. So this field, you know what I mean, right? So were this to be like a U1 gauge transformation, it would be a gauge transformation by alpha of x. So that the alpha coordinate would be a space coordinate. Okay, so this will really be some functional integral, but anyway, I'll just keep calling it dx and dba, d lambda a, dc.
Alpha is the direction of the gauge.
Alpha, no, but these are position dependent gauge transformations.
Yes.
So, were we dealing with the standard, let's say U1 gauge theory, then, and phi was a field of charge 1, then delta phi would be equal to alpha of x, phi of x. So there's the transformation, the coordinate is x. There's an infinite number of parameters here, infinite number of alpha variables, labeled by which point x.
And the number of alpha is the number of gauge group. Gauge group integration.
The dimension of the group.
Yeah, that's what I mean.
Well, the number alpha is the dimension of a group times number of points in space-time.
Yes, alpha has an x, but
It has an x plus other things. But because it also has an x, these will turn out to be functional integrals. It's integrals over functions. Okay? So I'm using very compressed notation here at the moment. It doesn't matter for purpose of my notation whether it's space index or other index, just to get the formal structure.
But the exponential, it's not an action. The argument of the exponential doesn't have any integral over anything.
Now it will have an integral because we're summing over all alpha.
And that will be a space-time integral.
And that will be a space-time integral. Yeah, because the coordinates alpha are space-time.
Yeah.
Okay, so we have dc alpha dba, okay, times exponential of minus I ba, I think we call it no, little b. Yeah, oh, this he liked to call b capital B. I'm sorry, this lambda he called ba. Okay, so IBA, and now this BA became a little BA, so this is BA times del FA by del phi I delta alpha phi I and C alpha. Okay? So now you see, what do we have? We have this delta function. We have this delta function, which we've exponentiated. So the full path integral we have to do. So this is the Fadi Popov. The full path integral, I'm writing it and you see if you believe me. It's this d phi db db dc exponential of minus the original action, which is a function only of phi. Okay, then minus put a plus, minus. Okay, he puts a plus, and so we have a minus in. He likes to write it as this. So minus I B A F A. That was this original delta function. Times the Fadi Popov thing. Okay? Okay? Times the Fadi Popov thing.
Why both the B's occurring?
Yeah, why are both the B's occurring? You see, this part of the board was only a trick for computing this quantity.
yes.
Okay? So once we've computed it, we put that this is equal to this.
Yes.
And then we put this back into the path integral.
Yes.
So there's this delta function and the Faddeev-Popov cost.
Yes.
And the delta function will be exponential.
Right. Oh, the delta function.
Okay?
Yeah.
Now, you see, this is a bit different from what we actually did in class. Because in what we actually did in class, we just straight away used the delta function
Yeah.
to do the path integral over some parts of the fields. I'm not going to do that. I'll do that only at a later stage. Okay? So right now we've got the full unfixed action. No gauge fixing done. Then this expression which was there to gauge fix. But we've not done the gauge fixing. We've not solved that delta function. Okay? And plus we have plus IBA del F A by del phi I delta alpha phi I C alpha. I'll just check his signs. Now he's rescaled, let's say B, to make this plus without an I into the, let's say the B. It makes no difference because
Yeah,
it's
in the
fermionic
path.
path integral makes no difference.
This is the same action, but we have just kept delta function.
What? Yeah, this is the same action. And now we've introduced 3 new fields. Capital BA, little ba, and little c alpha. These 3 new fields, once we've integrated this, in principle everything should now be good. Because we have introduced the delta function. So now, there should no longer be the integral over the extra gauge orbit. That integral should be sort of trivial. Okay? And that we see immediately. I mean, anyway. Everything should be good. We may have to do some processing now to see that it's good. Okay? What the difference in class is that we didn't do this step. We didn't introduce this delta. We just used the delta to do the path integral.
Yeah. So this is the S goes. This is the BCCFT.
This is the BCCFT. This is this. Now, if we do what we did in class, we would have done this with capital B integral to get delta function in FA, and then use the delta function to do the integral over the metric. This is an unprocessed version of what we did in class. You can imagine doing that. Okay? Excellent. What? You are looking what the BRST symmetry might be? Yeah, that it will be. It will. Exactly. Exactly. Exactly.
So the C alpha and then C will go to C. C will go to
A bilinear in C's.
bilinear in C, then you will use FABC, right? Otherwise, I am trying to say that yes, I should be BRST, it will be invariant, right?
Yes. Yes. You've got the structure exactly right. I'm going to show that to you.
Yeah.
Okay. But at the moment, just let's look at this path integral. This is the path integral we have to deal with. Okay? Now, what Indranil was after and what we're going to try to see is that this path integral looks like it's some crazy thing, right? What we started off trying to do was to eliminate a gauge freedom, and what we've ended up with is all the original phi's and more. Looks like we've gone in the wrong direction. So how do we see that this path integral, which has so much enhancement, actually is doing what we want without actually doing some integrals? The great thing about this integral is that it has a new symmetry, which is now what we're going to study. This is called the BRST symmetry. Okay. So, consider the following symmetry. Consider del phi I is equal to C alpha delta alpha phi I. And maybe I need an I, but I minus I. minus I, and I'm going to put an epsilon here, just, it's a formal anti-commuting parameter, formal small parameter. Okay? Delta BA is equal to 0. Delta BA is equal to epsilon BA. And delta C alpha is equal to F alpha, C alpha is equal to, right, I by 2. F alpha beta gamma. Now, how do I write this? Let's call this gamma. Yeah, we put the special index first, the other two indices here. Alpha theta phi, C theta, C phi. Epsilon. Epsilon. Everything has an epsilon. Correct. The i's have very little meaning. You see, we could absorb, I think we could just absorb them away by a C goes to IC type. Yeah, you see the i's only appear when when the number of C's on the two sides are different. So here you've got one C, two C's. You can get rid of them if you choose just rescale C. Yeah. So it's just a matter of convention. Okay. Now, first thing I'm going to claim is that this is a symmetry of our action. Okay? Let's check that. Okay, so I'm going to write this action as S1 plus S2 plus S3.
Is there any way to derive this symmetry from, let's say, the another current action? Because I've always seen this symmetry just stated and then.
Well, you know, usually what you do is derive a Noether current from the symmetry.
Right.
So you have to first see that there's a symmetry.
Yeah. No, I mean, the
Well,
way it's put is somewhat arbitrary. I mean, as if the symmetry was just handed to us.
Well, there's this action. Yeah, so why? Oh, yeah. Yeah, well, see, what you want is something that's related to gauge transformations. You want a fermionic symmetry. You know, C started its life as an infinitesimal gauge transformation. So this is an extremely natural thing. This is just a gauge invariance of the action under phi. Okay? So what you want to do is to promote the usual gauge invariance to a fermionic gauge invariance with a parameter C.
And in the first line you have no choice other than C. Because the alpha is none of this beta or A or BA carries A. You have only choice is C. And then once you have put C, you have to put a fermionic picture because C is fermionic and phi is actually sort of, you don't want to change the nature of phi.
Yeah. And then, you know, so this part of the action, whatever it is, will automatically be invariant. That just follows from gauge invariance of the original action. So all that remains is that these two now have to be gauge invariant, have to be BRST invariant by themselves. And then you basically adjust these to make that happen. Okay? It's not, let's just check that it happens. I don't think there would be too many choices, basically. Okay, let's just see that it happens and then maybe we can try to explore what else you could have done. But it's basically trying, if you've got an action and generically actions don't have symmetries. So if you've got a symmetry, it's a special thing. You just have to find it. Okay, I don't know. There may be something more to say. I don't know. Okay, so let's first look at, so let's call this is S1, this whole thing is S2, this whole thing is S3. So that our path integral is integral all the fields e to the power minus S1 plus S2 plus S3. And what I want to show you is that S1 plus S2 plus S3 is BRST invariant. We've already seen that S1 is BRST invariant. That was obvious.
Part of S3 is cancelled.
Exactly.
Only part is leftover part of S3 is invariant. That is probably
Jacobi identity. I think it's even easier than that. Let's just see. Maybe it's Jacobi. I'm not sure. Yeah. Okay. Let's see. So first, let's look at this term. What is delta S2? Delta S2, well, BA doesn't change. So the only change is because FA changes. Okay? So that's equal to minus I BA. And then F changes why? F changes because phi changes. So that's del FA by del phi I. And how does phi change? It changes by this. Okay? So minus I epsilon C alpha delta alpha phi. Is this clear? Now let's look at S3, the change in S3. The change in S3 comes from two sources. There's the part from BA, which is the part Indranil was talking about. Yeah, which was, so now BA was epsilon BA, epsilon BA times del FA by del phi I delta alpha phi I C alpha. Yeah. Now you see minus I times minus I is minus I times minus I is minus 1, and capital BA was bosonic. So you can bring the epsilon through outside without picking up a sign. So this minus cancels this plus. Okay? So this term in the variation of S3 cancels that term in the variation of S2. See, you choose these to make sure that these two things happen. Okay. Now what about the other two terms? Well, why do I say other two terms? Firstly, because this quantity here in S3, we've already taken into account the transformation of BA. We have to take into account the transformation of phi's and of c's. Okay? So now the remaining change is the change in it's BA times delta of del FA by del phi I del alpha phi I. Actually, let's write this whole thing. Let's write condensed notation for this whole thing. Let's call this whole thing delta F. You see, we just want to show that this part is 0. So there's some up to some minus i's. This is delta alpha F. The change in F, of course, induced by the change in phi. Okay? The change in F times C alpha. This will make the algebra easy. We want to look at delta BRST, the BRST transform of the subject. Okay. So let's see, how does it go? This is BA. Now the first thing. What? Exactly. But we haven't yet shown that delta square is 0. Yeah. Exactly. It is. So now let's look at this quantity. This quantity has two terms. The first thing is acting here. So that's it's C beta del beta minus I epsilon C beta del delta beta of delta alpha phi, delta alpha f. Right? Because it's this change and then small change. Because this means, you know what it means, right? It's the derivative times change in phi. Okay. And then plus there is delta alpha f and then change in the C. Okay, so that's that is now what? Change in C was delta alpha f plus I epsilon. I've taken that through the f's because it doesn't matter. Plus I epsilon times change in by 2 times f alpha theta phi c theta c phi. Yeah, where I made some mistake. Yeah. Well, there was a C alpha here. Thank you. Okay. Now the next thing we do is to note that this quantity here, this can be taken here. Everything here is cosonic. This quantity here is by itself antisymmetric. So this is no, it's not 0 because but it can be replaced by anti-commutator of delta alpha, delta beta, anti-commutator by 2. So this part is this by 2. Okay, and then that gives us f. That gives us f gamma beta alpha commutator, sorry, commutator times delta gamma of f. Okay, and there was a by 2. And now this should just cancel if we've done things right. Yeah, it's just cancelling. These are identical terms with a minus sign. Right? Let's take this guy here. Basically, this guy contracts with the upper index of the f in both terms, and the c's are arranged so that the first index and second index contract with first index and second index in both terms. But there's a relative minus sign between the two, and therefore it cancels. Okay, so that's equal to 0. Okay, so we've demonstrated that this action is invariant and this has this symmetry.
Using the fact that commutator is f antisymmetric.
Huh?
Using the fact that f alpha beta is antisymmetric in alpha beta.
Using the fact that f alpha beta is antisymmetric in alpha beta, correct.
That is the statement.
Yes.
With this you can prove that.
I mean, it's related, but yeah, you wanted some product of two f's, right? I mean, here we've got linear in f. We're going to use Jacobi identity, but to show that this thing is nilpotent.
Yes.
That's where the Jacobi identity will be used. At the moment, we don't need it. Okay. Yeah. Okay. All good. Okay. Excellent. Now, the next thing I want to show, and I will leave it largely as an exercise for you. We'll just I'll do the path that Indranil was referring to, since we can use the Jacobi identity then. The next thing I want to check, just an algebraic exercise, is this remarkable fact. We will give a physical interpretation of it in a bit. But the remarkable fact is that if you act with delta twice, okay, so suppose the first one was you act with delta with some epsilon 1, and then you act with delta with some epsilon 2. Epsilon 1 and epsilon 2 are just some arbitrary anticonverting number. Okay? And then write this as epsilon 1, epsilon 2 times whatever. Let's call that operation delta square. The delta square is 0. Okay? Which says that the generator of this transformation, whatever it is, squares to 0. This is what I want to show. Yeah, so it's exterior derivative on what? So you want to write this as d of on something. As you know, in the context, in some contexts, supersymmetry, in context of sigma modules, supersymmetry operators can be written as exterior forms. And twist, in some contexts, there's contexts where you twist supersymmetry to get a BRST symmetry. In those contexts, if you basically gauge the supersymmetry. Okay. In those contexts, a BRST symmetry takes a form. There may be some formal way in writing it, some form thing, but not that I know of in a useful, not in a, unlikely you'll get some familiar form statement. Okay. Now, what do we want to check? We want to check that this thing is 0. So you act with this operation twice and you get 0. And we keep this epsilon 1 and epsilon 2 just to keep track of signs. Okay? So what do we have to do? What we have to do is to act with this twice. Just to act on each field twice and check that you get 0. Okay? So let me do a couple of them. And I'll leave the rest for you to check. This one's the easiest. This one's pretty easy. Because you act on this and you get 0. Okay. What about this one? Okay. It's quite easy, so let's do one. So the first delta epsilon 1 on phi was equal to minus I epsilon 1 C alpha delta alpha phi I. Now we'll act with delta epsilon 2 on this. Okay? So what we're supposed to do is to put an epsilon 2 times delta of all of this. Now delta of epsilon 1 is 0, so minus I epsilon 2 epsilon 1 times delta of C alpha delta alpha phi I. Okay? So we just want to check that this is 0. But this has two terms. The first term is, let's take the change in C. So that is plus I by 2. I've got the epsilon out. No, I should be careful about my epsilon 2s.
Yeah.
Should I be careful about my epsilon? This is always the confusing thing. Just a minute. Yeah, I should be careful about my epsilon 2's. I should be careful about my epsilon 2. So let me do this carefully. Let's call this delta epsilon 2. Okay, so this is minus I epsilon 1.
So we are also assuming that delta epsilon 2 while going to epsilon 1 doesn't have any sign.
Yeah, delta epsilon 2 because you see the change in phi is fermionic.
Yes.
And epsilon is also fermionic.
Yes.
So if you keep track of the epsilon 2's, these are bosonic things. And all the signs will come in taking the epsilons out. So that's the point of keeping track of these things. Is this clear? So if I keep the epsilon 2 in this is a bosonic operation. It goes through everything. But the point is it will produce an epsilon 2 here. Then I'll bring that epsilon 2 out. Well, let's watch how it works. That keeps track of the signs. This is one formal way of keeping track of the signs. Okay, so we've got minus I by epsilon 1 by 1. Let's look at this guy. This was delta epsilon 2. So this, let's act first here. So epsilon 2 acting here gives us I epsilon 2 by 2 F alpha theta phi C theta C phi. Delta alpha phi I. Okay, and then the guy going, the other one was, which is C alpha, and now we will have delta minus I epsilon 2 C beta minus I epsilon 2 C beta delta beta delta alpha phi I. No, overall number. So, wait, I want to keep track of every relative number.
Not overall, right?
Overall, I got the overall number wrong though. Oh, there was. Thank you. Yeah. Not that it will matter, but good. Okay. Now, once again we use the same trick. Okay, delta beta delta alpha can be replaced by commutator divided by 2. Okay, so that's F beta alpha zeta. F zeta beta alpha delta zeta phi I by 2. Okay, and now let's see. Beta alpha.
This epsilon 2 on being shifted to the left of C alpha.
Epsilon 2 is shifted to the left of C. Yeah. It's 0. Why is it 0? I'm getting the opposite.
You take it on the left.
I take it, so that makes this plus.
The alpha beta
Plus
exchange.
yeah.
Notice that the orderings are opposite.
And the ordering is opposite. That I didn't see. Yeah. So beta alpha.
Alpha beta.
Yes, exactly. Alpha beta. So it's 0. Right. So Indranil pointed out that these are contracted with alpha here and beta here, whereas these are contracted with theta here and phi here. So if we switch the order of the C's, we pick up an extra minus sign, so we get 0. Okay, so this is equal to 0. Still no Jacobi identity, but it's coming. Okay. The last one's clearly going to give you something bilinear in C's, in F's, right? Because it already has an F, and so we'll yes. Okay. Now the last one is to do delta epsilon 2 delta epsilon 1 on C alpha. Okay, let me just say it schematically. I'll leave you to work on the details. See, basically you've already got an F, then you act on the C's, and you get another f. You get two f's times a c. Two f's times you'll get two f's times three c's. You'll get two f's times three c's. Okay? Now, when you do this, you pull out those three c's out. This product of two f's will come in a combination that will be that will have the symmetries that are relevant to the Jacobi identity. And so the Jacobi identity will make it 0. We could do that, but it's painful and we won't learn much better. Okay, so let's. Yeah, I'll leave. That's an exercise for you guys. Okay? Fine. So what have we learned so far? Okay, what we've learned is that we've got a symmetry, and that at least at this formal level, it's nilpotent. That is, you take this suppose we've got a generator of the BRST symmetry, we call it QBRST. We have QB square is equal to 0. Now there is a third bit of algebra that I have to do, and then we can get back to physics. And the third bit of algebra is to notice the following, sort of almost obvious fact. Let's remember what was, oh please help me. So S2 plus S3 was equal to, was it BAF, please help me get the signs right, BAFA plus I BA del FA by del phi I del alpha phi I. Yeah, let's call this whole thing, let's always call, anyway, okay, del alpha phi I C alpha.
And there was a minus I derivative over there, yes.
Minus?
Minus I.
Minus I.
You can't get a factor of I because your del B does not have the right.
Yeah, I'll just check.
You cannot have a factor of I.
Yeah. S2 had minus I and this, okay, so I got this wrong. Minus I
Yeah, that's what it is.
plus, thanks. Yeah. Okay, this whole thing, let us just call as usual, let's call this delta alpha phi, delta alpha f. This is shorthand for, you know what we mean, right? So f changes because phi changes. It's shorthand for this derivative. Okay, now the thing I want to show you is this. The thing I want to show you is that this is proportional to, in fact, is proportional to delta of BAF. In order to see that, we'll just compute delta of BA. So let's compute delta BA. So that gives us the first term. So that is equal to epsilon times BA, sorry, capital BA FA. Okay. What? Yeah, it had to be invariant under BRST, but it didn't have to be BRST exact. That is, BRST exact is a little more information. Right. And then the next term is when we is what? Is plus BA epsilon times change in FA. Okay. Now change in FA is because of change in epsilon, so it will get delta alpha F times minus I C alpha.
shifting the epsilon to the
Shifting the epsilon to the left changes the sign. So we get
yeah, and some overall sign.
Yes.
But if we pull out I epsilon.
I epsilon. This is exactly this thing. Right? So this comes with a plus I epsilon. We put out a plus I epsilon, that puts a minus I epsilon here. That's exactly this. Yes, we can set different. Coming. Yes. You can choose different FAs.
For all different FA, your physics should not alter.
Yes.
Final physics should not alter.
Yes.
Is it not equivalent of saying it has to be exact?
Yes, exactly. We'll be showing this through algebra, and then that will be the physical consequence of this algebra. Yes. Okay. And so we've seen that S2 plus S3 is actually what is called BRST exact. That is the BRST operator acting on something else. Okay? So let me summarize, and then we will draw consequence. What we have shown is that the effective action is equal to S1, which is the original action, plus S2 plus S3, which is equal to S1 plus delta BRST of BAFA. Okay, times some number.
Yes, some anti-commuting number.
Yeah, but the action itself, just remove the epsilon basically. By delta BRST, I mean the part without the epsilon.
Okay.
Set epsilon to unity. That's what we got from here. Here, of course, there was no epsilon. Right? I mean, so say that the BRST transformation is epsilon times delta B. Okay, suppose we think of it as an operator. Epsilon is a parameter, and then there's the operator. Okay? Times this business. Some number I minus I doesn't matter very much. Okay. And we have shown that delta B square is 0. Okay. Now why is this important? This is important. And of course we've shown that the whole thing is invariant under BRST. Now, by the way, now that we've shown this and this, then the invariance under BRST transformation follows from these two statements. Okay? Because S1 was invariant because it was acted like gauge transformation. And this is invariant because you get, when you act on it, you get delta B square. And delta B square is 0. Is this clear? Okay? It's sometimes nice to think of an operator QB whose action on anything generates delta B. Epsilon times QB generates epsilon times delta B. Okay? So what we've got is that S is equal to S1 plus some number times QB BAFA. The number is plus I minus I, doesn't matter, some number. Okay? And then when we act with another Q on this part is invariant. And this is invariant because we get because Q squared is equal to 0. Now, the key point is the following. As Indranil said, well, let's start with various things. Firstly, suppose we are interested in doing this. We are trying to compute plus Q whatever. We're trying to compute this path integral. Okay? And I take this I. Okay? I take this I and I replace this I by, okay, suppose I do this, okay, wait. Now, let me start this way. As Indranil said, okay, as Indranil said, changing F is an issue of changing gauge. What we want to do is to look at a set of observables that are not affected by changing gauge, because those are the physical observables in our theory. But because we've got this Q structure here, in general when you change F, you change your path integral and you'll change this number. Let's examine that in more detail. What is the change in this number because of a small change in gauge? Well, that change will be proportional to, so change in matrix element, change in MFI is proportional to F times e to the power minus blah 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 everything times what you get by changing this object. Okay, so Q commutator, something which is BA delta FA, or you can call it delta anyways. You can think of it as Q commutator BA times I. Right? Because I've done a change in FA, so that part changes a bit, and then you bring it down because you're looking at the infinitesimal change. Okay. Now in general we said that this is 0. But there is one situation, this is non-zero, but there is one situation in which it will be 0. The situation is, if we look at states, exactly, if we look at states I and F such that Q on I is equal to Q on F is equal to 0. By the way, Q is a Hermitian operator.
Maybe that is why they are putting I. No?
Well, for i's in the action, Q is a Hermitian operator because of the reality properties of the field C alphas. Let's say C's were originally gauge transformations. So we work with a basis such that all the gauge transformation parameters were real numbers. Okay. Similarly, B's were some real functions. Okay. Just tracking through the reality properties of C's and B's tells you Q is Hermitian. That involves putting some i's. I mean, of course, once you have C with some basis, if Q, yeah, it's true that if you see the action of Q is chosen so that it's Hermitian. Now, what your field redefinition variable is basically irrelevant to that action. I mean, once you have Q Hermitian, you can change your field variables to whatever you want. It won't change that hermiticity. But it will be more straightforward to see the hermiticity of Q in the variables where C and B were relevant.
You said that Q operator is Hermitian, that you can see from its action itself.
I think so. You can just see, I mean, for instance, the classical version of the statement is that it's a real operator. That is, you act on the complex conjugate field and you produce the complex conjugate action. Okay, there's a bit of definition going on here because you have to know what your complex conjugate of C is in order to make the statement. You need to know these properties. So you let them inherit the complex conjugation properties of the things that they stood in for. The infinitesimal gauge transformations. And from that you will see this. You see, had Q not been a Hermitian operator, then its Hermitian conjugate would also have to be a conserved operator.
Yes, yes.
And there's no second symmetry in this theory. So if you're worried that you're fooling yourself in some way, that's a good way to convince yourself. Because since there's only one operator, it had better be self-Hermitian. But anyway, you can track it down just by looking at reality properties. Okay, but that I agree that argument is involves some definitions and so on. I find the most convincing argument just this one. That there had to be two symmetries if it was not Hermitian. The complex conjugate of this would have to give you another symmetry. And then might proliferate. But this is the unique operator, so better be. Okay, fine. So see, now suppose you looked at states such that I was annihilated by Q and F was annihilated by Q. Now, for such states, when you look at the action on such states, this quantity is 0. Why? Because there are two terms in this quantity. One in which Q acts on the right, and that annihilates I. And the second in which Q acts on the left, and that annihilates F, because of the hermiticity of Q. Okay? So we've identified something. We've identified a set of states which, if we somehow declare that those are the allowed initial and final states in our problem. Okay? Then for those states, the inner products, the transition amplitudes, are gauge invariant. We've just proved it. Using the fact that Q squares to 0. Sorry, using the fact that, just using nothing at the moment. Just using that Q annihilates the states of the Hermitian. Is this clear? Okay. Moreover, something else nice happens. Now suppose we take the state I and replace it by I plus Q times some j, as Q times some k. Okay? Then at least for the straight path integral. So I look at this term, this thing here, and I replace I by I times Q times plus Q times some k. Now let's look at the path. I want to see how this matrix element has changed. So that's the same as computing the matrix element of F with the path integral, with this business, okay, times Q times k. Okay, but this path integral is some Hamiltonian evolution from this to this. The Hamiltonian commutes with Q because Q is a conserved operator. It's a symmetry. So you can take this Q through here, and then that annihilates F. Okay, so this in some operator language is some Tracy beta, some evolution by Hamiltonian, which commutes with Q. So it's a conserved operator. Okay, and therefore you see that two states that are related by this, two states that are related by the difference between these two states is Q acting on something else, give you all the same inner products. So I and I prime, let's call this thing I prime, the inner products of this with any other state, transition amplitudes, these transition amplitudes are invariant under this shift.
With any other BRST closed?
With any other BRST closed state. So first, we have found the rule that we will only allow all our states to be BRST closed. So Q on state equals 0. Because otherwise you won't get something gauge invariant. Once we have made this rule, it follows immediately that any state and its and if you add to that state Q times something, it will have the same, that will not change its inner products with any other physical state. So states that are annihilated by Q BRST will be called physical states. Okay? Now, the set of physical states gives you the same inner products with any other physical state if you change any one of these states by Q times something. Since, okay, now the
one conserved fermion switching for symmetry.
hmm?
Is this procedure goes through?
Yeah, sure. Oh, sorry, one conserved fermionic, what procedure?
This statement that the state
Sorry, we do have only one real Q. What? I didn't understand.
Suppose we have a theory
Uh-huh.
in which we have supersymmetry, and
Suppo-
there is only one real supercharge.
And we have only one real supercharge, and Q squared is equal to 0.
Say Q square equal to 0.
Okay, that's it.
And then this manipulating the first statement that Q acting on this state is 0 is then this state becomes supersymmetric.
The state is supersymmetric, correct.
This is okay, done. Now I want to see what is happening to the upper box.
Yeah, so something very similar. There's this thing called the chiral ring. Yeah, so the chiral ring is, it's in a more realistic context than this one supersymmetry. Okay, I'll tell you the context. Suppose you look at an n equals 1 theory in 4 dimensions. Then the supersymmetries are the Q's and the Q bars. Let's look at all states that are annihilated by both Q's, but not necessarily both Q bars.
Okay.
Let's call that the chiral ring. Okay? Now within the chiral ring, for reasons like this, you can show that that states within, it's basically Q cohomology that dictates the chiral ring.
Only Q cohomology.
Q cohomology.
Q bar.
Yeah, yeah, exactly.
Within that set because of the
Same arguments. Yeah. So this kind of thing, often when discussing supersymmetry, we have similar reasoning. Yeah. Okay. Now where are we? So far we've been looking at just straight path integrals. But we may want to put some operators, so O1, O2, O3, and so on. Okay? Now, let us suppose that our O's, I want to do the same thing. I want to
So one or two
operator insertions.
any operator.
At the moment, any operator insertion. Okay? But if I choose my O's to be annihilated by the QBRST transformation. Okay? So if I choose my O's to be annihilated by the QBRST transformation, okay, then once again all these inner products will be and these i's and f's also to be annihilated by BRST. Then once again all of these matrix elements will be gauge invariant, because you'll pick up factors like, let's say, of QB times something here, and then we can just take the Q through here, through these O's as if they don't exist, because they commute with the Q's, QBRST. Yes, exactly. And moreover, if you act with this equivalence of I plus I with I plus Q times something, also goes through when these O's are commute with the BRST operator, because all you want is to be able to take the BRST operator through the Q's, through the O's, and you can do that because they commute. Is this clear? Moreover, suppose I take O and replace O by O plus Q commutator something. So let's say I take this O1 and I replace it by O1 times plus Q BRST commutator phi 1. Well, let me do it for O2, just so you don't think I'm choosing a special guy. Now this has two terms, one of which the Q is to the left here. Phi 2 need not be BRST. In fact, it's not, right? Otherwise this would be 0. Okay? But because it's to the left, I can take this Q through here and kill the F. In the other term, Q is to the right. I take it through there and kill. Hmm.
You said Q,
Hmm?
but if you want to annihilate from the left, you need Q diagonal.
But Q is Hermitian.
Like, you just give me an example in n equal to 1.
Ah, in the n equals 1 theory. Give me a minute. Yeah, this chiral ring operator though, I mean in the chiral ring, you act with the vacuum and various operators. So the chiral ring is a set of correlation functions of these. So then this is annihilated anyway. Yeah, so if it's true, if you want to do something more general, it won't go through. Yes, it's just the vacuum correlators of the superscript. I would have to remind myself, there may be something more to say. At least, okay, I think what I said is right. There may be a little more to say. Okay, but let's continue. Yeah, exactly. And because you've got a different notion of complex conjugation.
The state can be written as vacuum and an operator.
Yeah, let's. Okay, excellent. So now what we have is the following. We've got, so you see that now if you take this operator, this is two terms. This is q phi 2 and phi 2 q. The one which is q phi 2, you take the q through to the left. The one that is phi 2 q, you take the q 2 through the right. Both terms give you 0. So you see that also we have this interesting thing about operators. We come to the rule that we're only allowed to insert operators that are q closed. By closed I mean annihilated by action of q. And if I replace an operator by an operator plus something q exact, which is the old operator plus q commutator, that's something, I don't get any new answers. Okay? So we come to the following conclusion. Both for states and for operators, we get gauge invariant answers for states and operators that are q closed. So f, these are physical states, these are physical operators. Moreover, we don't get any new answers. We don't get any new answers for states that differ by f and f plus q chi, or operators that differ by O goes to O plus q phi. So the set of physical states is identified by what is called the cohomology of the q operator. That is, the set of all states that are annihilated by q modulo the states that are q exact, that is q on something else. Well, you see, the point is that there is one very easy way to make states that are annihilated by q. Just act with q on any other state. Because q squared is 0, q acting on any other state will obviously be annihilated by q. But that's very easy, it's too easy. All such states don't give you anything interesting. You just take such a state, its inner product with its matrix element with any other state is 0. Okay? So the set of physical states is identified by all states annihilated by Q, modulo states that are Q exact. So it's identified with equivalence classes of states. Okay? And the set of operators is identified by operators annihilated by Q, allowed operators annihilated by Q, modulo states that are Q exact. Is this clear? Now, you know that, let's say the operators have to be annihilated by Q, is not a terrible surprise, because it's some generalization of the idea. It's some generalization of the idea that the operators built out the original matter degrees of freedom had to be gauge invariant. Because if you act on an operator built out of the original matter degrees of freedom with the Q operator, it just generates a gauge transformation of that operator times C alpha. So the way that is annihilated by Q is that is gauge invariant. So this is just a generalization to include, to allow including contribution with ghost fields of the notion of the operators being gauge invariant. Okay? And yeah, and that these let's stop this here and we'll come back. Okay, excellent. So this is going to be this is the general rule when we do BRST quantization. Okay, you work with this much enlarged Hilbert space, but you only allow yourself to compute quantities which correspond to states and to operators that lie within BRST cohomology. Okay? Any questions or comments? Otherwise we'll turn to using this for what we're interested in. Fine.
So these states I and I plus Q here, are these two different physical states?
No, they're the same physical state. So physical states, I mean states, really physical states, are identified with equivalence classes of states. And two states are said to be equivalent to one another if they differ from one another by the action of the state. Okay? And they're not physical because they're not distinct because the inner products between this state and any other physical state, it doesn't care about this shit. Okay, notice by the way that we've already seen that F is a physical state and chi is any state, then this is equal to 0 because you can act the Q on F. Okay? Now, this is true for every physical state. So in particular, it's true for F is equal to Q chi. And therefore, we have norm of Q chi is equal to 0.
But F was supposed to be a physical state, right?
Oh yes, it was. Oh, F was any state annihilated by Q. Right, because that's all we used. So I'm sorry, sorry, F was a state, let me say it more precisely. F was a state in Q was Q closed.
Now, if
F is Q chi, it's clearly Q closed because Q squared is 0.
I mean, we are taking F to be one state. I mean, let's
To be Q chi.
Yeah.
Yeah. Chi Q chi is equal to 0. This is obvious because Q squared is 0. So every state that is Q exact is a null state. Okay? This is another way of seeing why these states, shouldn't have been physically okay. They're Q closed, but they're null. So if you want to, if you want to get some good physics with a good positive definite Hilbert space, these states should be fun. Okay? Okay, great. So let's move now. and let's complete our discussion. Okay, what we're going to do as a warm-up to the application to the path integral for the string is to apply these ideas to the particle world line action path integral that we started our lectures with. Okay, so let me remind you. Okay, let me remind you that the action for the particle world line theory was let's see, integral x mu dot by E, where E was and let's take a half, plus E m squared again by 2 I believe. Okay, yeah, so let's take the half outside here. This was the action that we very early on in our lectures we started with, which was the Polyakov version of the action, which was just the square root x mu dot x mu dot. Okay, and our first lecture in this course started by considering this action and quantizing it in many different ways. Okay, now we're going to return to that problem by quantizing this in yet another way, by using BRST quantization. Okay, so let's see. So in this problem, what is the invariance of the problem? Well, the invariance is simply world line diffeomorphisms. Okay, so consider, let's remind ourselves what these diffeomorphisms were. So suppose we had some epsilon of tau, or maybe I'll call it v of tau, just so that at the moment it's bosonic, which was an infinitesimal change of variables, right? So we have this is d tau. Okay, so we have tau is equal to tau prime plus v of tau, and v is some infinitesimal quantity. I got v of tau prime. Okay, v is infinitesimal, so whether it's tau or tau prime.
And there's also the scaling diffeomorphism plus the equivalent of phi, some scaling of tau. So.
Well, in the particle world line action, we had no, the only symmetry was diffeomorphisms. It's because this E explicitly appears. In the particle world line action, the only component in the metric was the while component, and that appears. The analog of that does not appear for the string thing. Okay, so there's a little more involved. Okay, but in the particle case, it was just diffeomorphisms. Okay, E is just the viewer by square root of the metric. It's like a one form. Okay, so under this transformation, I want to understand how each of these fields transforms. Okay, so what about x mu of tau? Well, I'll just rewrite it in terms of tau prime. So that's equal to my x mu of tau prime plus v of tau prime. Okay, which is equal to x mu of tau prime plus del x. There's only one thing. X mu dot tau. X mu dot times v of tau. Okay. So what is the function x mu of tau prime in terms of the function x mu of tau? Okay, it's x mu of tau minus del as x mu dot times v of tau is equal to x mu of tau prime. Okay. Yes, but the difference between tau and tau prime doesn't matter. Okay, and therefore delta x mu of tau is equal to minus x mu dot v of tau. let us also apply the same rule to see how this E transforms. Okay, so let's remember what. So we have a metric. So E squared d tau squared. So E d tau basically is equal to E prime d tau prime. Okay. Now, what is the relationship between? So there are two changes in E. Well, this. You see that there's the change in E just because its argument changes. That's exactly the same as this. But there's also a change in E because of this rule. So the sum of the two gives you the full change in E. Okay, so let's compute the part because of this rule.
So that is will be closed. Commutator of the vector space on any manifold is a vector space. It is a rubber derivative coming in cancel. Therefore, this algebra diffeomorphism will be closed. It is closed by any means, but two diffeomorphism gives a diffeomorphism.
Yes.
This is the statement.
Yes, and we'll figure out which diffeomorphism you get. It's going to be E1 E2 dot minus E2 E1 dot. V1 V2 dot minus V2 V1 dot. Yeah, the other way. It's going to be that thing. We'll figure that out in a moment. But first, let's see how a single diffeomorphism acts on E. Okay, so E d tau is equal to let's write this as d tau prime plus v prime of tau of tau prime tau doesn't matter because it's first order. Okay, that is equal to E prime d tau prime. D tau prime. And therefore, delta E prime, so delta E, so and therefore E prime is equal to E into 1 plus V prime tau. Okay. And so we conclude that delta E so that we conclude that E prime of tau prime minus E of tau, the change in E, oh sorry, E, yeah. Now we should be a bit careful. We should be a bit careful. Have I done this? This is always, give me a minute. I just want to check that I got the signs right. What I really want to compute is x prime of tau. What I really want to compute is x prime of tau minus x of tau. That's the change in x. Now, at the same argument. Yeah. Yeah. And so I've done this wrong. Let me just do this thing again. Sorry. Right. So suppose I have x mu of tau. we've got this. It's true that x mu of tau prime plus v of tau prime is equal to x prime of tau prime. This is true. Now I want to compute x prime of tau prime minus a, let's say ignore the mu index, it's just, and therefore x prime of tau prime minus x prime x of tau prime. This is what I want to compute. Is equal to x prime of tau prime minus x of, I would have to move this tau prime by minus tau prime minus v of tau prime. Minus, right? Which is equal to plus, so I'm sorry, I'm going to mess up, x dot of tau prime because it's minus and there's a minus here. Times v. I wanted the sign, I got the sign wrong. Okay, so now let's look at this. Now you get the same quantity from here. So this is, I wanted a tau prime, yes, everything's a tau. Now I want to compute e prime and tau prime minus e of tau. Tau prime. Thank you. Minus e at tau prime. Now this has two terms. One term is just this. So it's equal to e prime dot, e prime to this order is the same. Anyway, e prime dot at tau prime times v. And then there was this term, which is plus v prime dot times e. That was this. Which is equal to d by d tau of v. Okay? And so we conclude, yeah, this is very easy to get the sign wrong. You just have to remember what you mean. It's the two different functions, but at the same value of the argument. Not the same points on the manifold, but the two different functions. It's very easy to mess that up.
This is some sort of isometry.
It's actually, we're just doing field theory. You know, we want to know, in the coordinate tau, if tau is 1, the function x in that coordinate differs from the function f prime and its new coordinate being 1 by how much? Please.
In the time manifold, x is a scalar field, and what you are supposed to do the linear derivative in that manifold.
In the time, what do you mean time?
Imagine this is a field theory in one dimension, but the one dimension is the time dimension, tau dimension.
Yes.
In this direction, x mu, every x mu is a scalar field, and you need the linear derivative of a scalar field,
Which is just a derivative, but
the mu index is not playing any role because
it's playing no role.
field in this manifold.
It's playing no role. The only thing that was,
Play a role in this because this is really a metric in this manifold.
the mu index still plays no role.
Not mu index is not playing any role. But in E you got a complicated answer
Yes.
because E is really a non-trivial tensor in this one-dimensional manifold.
Absolutely, as we saw from here. Yeah, absolutely. So all we're doing is to see how this thing changes under diffeomorphisms, how a scalar changes under diffeomorphisms, and how a tensor changes under diffeomorphisms. Now that's all we're doing. It's just that operation. But that operation, yeah, either you could work it out by using some formula, or you work it out carefully. And it's important that I remember that this answer was a total derivative. So anyway, I got it wrong if I got the signs wrong. Yeah, it's probably,
Because of the other term, En square has to be Lee.
it's basically some Lie derivative of,
It's exactly the Lee derivative of the
Oh.
complex function.
but it's not even a very complicated, it's just one index down. So one form. It's a Lie derivative over one form in one dimension is this object.
This object, and in this action, because E times N square, that part has to be invariant. It is better be a total derivative.
This
E
had,
times N square.
okay, good. That had better be a total derivative for that reason. That's a good argument. Yeah, that's a good argument. This should transform nicely. That's a good argument. Yeah, in fact, it will be relevant for BRST invariance of this whole action. Okay. So now we understand how each of these fields transforms under diffeomorphisms. Okay, we understand how each of these fields transforms under diffeomorphism. And now what we want to do is to apply this whole BRST procedure to this. Okay. So the first thing that we need, if we want to follow exactly the presentation I gave you, was to break the gauge transfer, this gauge parameter V of tau, to write it as a sum over. First thing I need is to identify the alpha index. Okay? So you can do it in many ways, but I'm going to do it this way just to be totally clear. I'm going to write V of tau to some function as delta of tau minus alpha V of alpha. Okay. So what I want you to see through this is that we're building up the tau function, starting with an arbitrary linear combination of some basis functions. The basis functions are delta functions. They're centered at different points, alpha. All I'm saying is that a function can be built up as something here and something there. Okay? And now this alpha is going to be our alpha index. Okay? Now, we had that, let's look at the action on fields. So, we had delta alpha on X is the action of this quantity with the function built out of V of alpha being just centered at some particular alpha. So it's this function delta of tau minus alpha. Okay, so delta alpha of X is equal to delta of tau minus alpha. Okay, times X dot at alpha, X dot at alpha, X dot at tau, it doesn't matter. Now, irritatingly enough, okay, I'll call this tau. Irritatingly enough, Polchinski here has a minus and here also has a minus. Yeah, okay, I'm sorry, Polchinski for some reason known only to himself puts a minus here, so we'll also have to put a minus here, because that makes no difference, right? Just
Minus everywhere.
everywhere minus. His V is minus half. Okay, so this is his definition of the coordinate thing. Okay, so fine. Okay, so delta alpha of E then is equal to, now what is this? This is d by d tau minus d by d tau of delta tau minus alpha times x of tau. So there will be two terms. One of them will go and hit this, and one of them will go and hit this. The one that goes and hits this will give a term that's very similar to this. The one that goes and hits this will give you a derivative of delta function. Is this clear? Okay. Now I'm going to ask, what is delta alpha delta beta? Is this clear? I'm going to ask, what is delta alpha delta beta? Well, actually, you know, we could, we could even work it out more generally. We could ask delta V1 delta V2. Let's do that because it's nice. Where V1 and V2 are arbitrary function diffeomorphism, then we'll apply it to a V1 equals delta of tau minus alpha, V2 equals delta of tau minus beta. Okay, so we can, you know, we can do it acting on any field. So let's do it on this guy. So delta V1, so delta V1 delta V2 on X is equal to, according to Polchinski, minus delta V1 of V2 acting on X, which was, of course we've got the minus sign, so V2 dot, no, V2 X dot, that's our minus sign here. Okay, and then delta V1 V1 of this, and then acting on any function, what we get is, so that is minus, so plus V1 V2 dot X dot plus V1 V2 X double dot. That's the first term. The term in the other order gives us these two terms in the other order. So if we take the commutator, we will get, can you see that this term cancels? Because V1, V2 is just multiplying. Okay? So these terms cancel, so this gives us V1, V2 dot minus V2, V1 dot acting on X dot. Okay? But we started with this Polchinski convention of a minus, so we find that delta V1 delta V2. So this is, of course, as Indranil was saying, it's another vector field, another diffeomorphism acting on X, but we've identified that with minus of this. So yeah, V2 V1 dot minus V1 V2 dot V1 delta of this. That's clear? Okay, and now we can apply this particular thing to the alphas. Okay, so let's choose V1 to be delta of tau minus alpha, and V2 to be delta of tau minus beta. Okay, let's do that. So V1 is equal to delta of tau minus alpha, and V2 is equal to delta of tau minus beta. So we get V2 2 v1 dot. So delta of tau minus beta delta prime of tau minus alpha minus delta of tau minus alpha delta prime of tau minus beta. Now, now I want to write this whole thing as okay. This I want to claim as the following. I want to claim that this is, you see, it's sort of clear that we're not going to get anything unless alpha is equal to beta. Right? So we're not going to get anything unless alpha is equal to beta. So I want to claim that this implies, I'll make a claim and then we'll check it. This implies that f gamma alpha beta is equal to delta of gamma minus alpha delta of gamma minus alpha del
Gamma minus beta and
yeah, sorry. Hello? Yeah. I'll be back by 7:30 latest. Okay, so maybe we can go around then. Okay, yeah, bye.
symmetric alpha
Yes.
And beta.
Yeah, it's del 3 del gamma del by del gamma delta of gamma minus beta minus delta of gamma minus beta del by del gamma delta of gamma minus alpha. Okay, I'm going to have to actually go very soon. Yeah. Okay. I want to claim that this is the case. Now, what does it mean to show that this is the case? What it means to show is that this thing times delta of gamma minus tau. Okay. What we have to show is that this quantity, we have to show that f gamma alpha beta delta of gamma minus tau minus gamma, no, that is gamma integrated, this quantity integrated over tau over gamma, the gamma no, yeah, is it working dimensionally? Let's see. First, let's see what it means, and then we'll check it dimensionally. You see, what we want to show is that this quantity, actually no integral, right? Was it integrated? Yeah, integrated. Yeah. the gamma is equal to this quantity, d tau minus beta delta prime tau minus alpha minus delta of tau minus alpha delta prime tau minus beta. Okay, this is the claim. Now let's check that claim. Okay, because we're integrating over gamma, we can use this delta function just to replace gamma by alpha. So we get d by d alpha. Well, that's right. Hello? Hello? Huh? No, the holiday is on Friday. Yeah. No, I can be largely at home tomorrow. I'll just, yeah. I'm in the middle of class now. I'll just call you back in Okay. Sorry. Yeah. So as Indranil said, what we will do is make this beta, and we'll make this. This was tau. Gamma. Yeah. This was gamma. So we'll make this alpha plus alpha. Now we do the integral. So with this becomes d by d beta delta of this. Gamma is tau. We switch a sign. So we'll get delta of this term will become tau minus what gamma, so with alpha, tau minus alpha. Okay? And tau prime of delta prime of tau minus beta. Is the sign working right? Let's see. When we do this integral, this term becomes delta of tau minus alpha. Sorry, let's say the first term becomes delta of tau minus alpha with a minus sign. Then we get del beta, but that's minus of, so plus del prime of tau minus beta. Which is the second term but with a minus sign. Yeah. Have I messed up on the signs? Let me check. We wanted this is with a minus sign, right? Delta alpha was defined with a minus sign. Okay, so now this works, and the other term will clearly work with the opposite sign. A flip of alpha beta with a minus sign. Okay? And so what we have shown is that our f of gamma alpha beta is this complicated object. Okay, with our choice of basis. We've chosen a basis for the space of diffeomorphisms. These functions of delta tau minus alpha. Now, alphas are just parameters. Of course, they're parameters on the rail, right? Times. So, f alpha beta gamma makes sense because these are parameter indices. With this choice of parameters, this was our structure. Okay. Now, let's very quickly finish this. Now, what is what is our action supposed to be? What was our gauge? You see, we will choose to fix e is equal to 1. So our f function will be e minus 1. Okay, we'll choose to do this at every value of tau. So fa, the a index is also a space-time index, a time index. Okay, and so S2 was equal to BA FA. Okay, so that is B of tau times E of tau minus 1. What about S3? S3 was equal to integral BA delta F delta alpha F C alpha with some i's. Okay. Now we need to know C alpha is just
1.
yeah. So we need to know what delta alpha F is. But delta alpha F is how F changes under an infinitesimal gauge transformation parameterized by the function okay.
Just the second one.
This one, exactly. Okay. So, and then we're supposed to multiply that by C alpha and integrate over all alpha. So let me just do that. So we'll get the sign right in a moment. I'll put that and then I'll put the right thing later on. This is BA delta alpha F, which was minus d by d tau acting on delta tau minus alpha. This was E. E of tau. Okay, times C of tau. Oh, C of alpha. This A index, I'm sorry. So this was also tau. Yeah. So the capital A index was really tau, and the C index was the alpha. Because we're setting function at every tau to 0. And these are the parameters of the infinitesimal. Thank you.
And there are integrals performed over both alpha and tau.
And there are integrals performed over both alpha and tau. Let's see. So what BA FA yes, over both alpha and tau. Exactly. Exactly. So now let's just do one of the integrals. So firstly we'll integrate by parts. If we integrate by parts, or maybe we can, okay, let's first integrate by parts. So we get B dot delta of tau minus alpha, E of tau, C of alpha. And then we do the integral over alpha. So we get B dot E of tau, that's it, C of tau, B dot EC integral B tau, and with some sign. Okay, yeah, and now we should actually work out the sign. I have to run. Oh, I'm going to ask you to check. Is that fair? Okay, it's fair. Please check the please check the sign. Okay. Now it depends. You'll find that we've got either got Pulchinski's answer or not, depending on whether you have the old version or new version of his book. The old version he had it wrong, and the new version he has it right. Like he had put the dot on the C in the old version, but that's wrong. And it's one of these things that Lubos Mortal pointed out. Okay. So this is the action. This. Sorry. Hello? 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 Yeah. Hi, Vikram. Very good. Vikram, I'm teaching a class at the moment. Can I call you back in like 15 minutes? Yeah, okay, bye. Okay, so this is the BRST action. Now, what we need to do, what I wanted to do with this action is to show you, illustrate the BRST procedure and get the same answer that we got, in 12 different ways in our earlier thing. But the real reason I did this in such detail is that in a relatively simple context, we see how it works. And then the generalization to the string will be relatively simple. Okay, we'll do that next time. Now,